Hi, I'm Christopher, a research software engineer with Research Software Workshops, and it's a very warm welcome to part 6 of Text and Sentiment Analysis in R. The materials at the URL below navigate to the Ngram section and it will look something like this. Now at the beginning of this workshop, we were looking at tokenizing texts, and we were tokenizing by an individual word. And I told you later on in the workshop we'll look at tokenizing by other things. Well, here we are later in the workshop. Now the token, when you tokenize text, is the smallest unit of text that you want to analyze. So it could be a word, a line, a paragraph, etc. But it's very common that you want to tokenize using tokens that represent multiple words, or actually really common, pairs of words. This is because words correlate with one another, and the choice of, say, the first word can significantly change the meaning of the second word. For example, putting not before happy significantly changes the meaning. Now a pair of words is called a bigram, and more generally a token comprising n words is called an n-gram or n-gram. Tokenizing on bigrams or n-grams enables you to capture and examine the correlations and most importantly the immediate context around each word. Now it's very simple to use UnlessTokens to tokenize on n-grams. So let's first start by loading up the Adventures of Sherlock Holmes. So we'll go into our studio. We'll create a new R notebook again. Close this down, remove this text. And then I'm going to save this. I'm going to call this ngrams in my workshop folder. Okay. So first thing we need to do is load up the packages that we want to work with. So we want the tidyverse, as we always do. We also want to have tidy text because we're going to be using the UnlessTokens function, and of course Gutenberg so we can download the books we're going to be analysing. So again, I'm going to bring up the Sherlock book, and I'm going to get this from Gutenberg download, and this is book number 1661. And I'm just going to mutate this as we have before to add in the line number. So mutating it where line number, the new column we're creating, is equal to row number. Okay, so that's now loaded up the Sherlock text. Now the UnlessTokens function accepts an argument that's called token. If I flip across to here, you can see this. Now this token that you put in as an argument can be one of a range of values, so it could be words, which is the default, and that will tokenize based on words. So if we did token equals words, it would do what the function does by default. You can pass in lines to tokenize by lines, sentences to tokenize by sentences, and indeed there's even a tweets which will tokenize by word, but will preserve usernames and hashtags and URLs if you're sort of analyzing Twitter data. Now the one we're interested in is n-grams, so we use token equals n-grams, and then we have another option which is n, and that will specify the number of words in the n-gram. So if we do n equals 2, that will mean tokenized by bigrams. So let's now put this into RStudio. So we're going to create a new tibble called Sherlock bigrams, which will be created by taking the Sherlock tibble and piping it through UnlessTokens. But now we're going to put, instead of putting the result into a column called word, let's put it into a column called bigram. We're analysing the text in the text column, but now we need to set the token type. So token equals n-grams, and then n equals 2. And then if we have a look and see what this would actually be once the calculation's been performed. So there we are. You can see what's happened now is pairs of words have now been tokenized. So you have the adventures of Sherlock, Sherlock Holmes, Sir Arthur, Arthur Conan, Conan Doyle, etc. The five orange pips for the man with the, etc. Now obviously these bigrams are full of stop words, and so we need to remove those stop words, but we can't do that straight away at this point because at the moment this bigram is literally 2 words in one column, and if we're going to remove by stop words we need to break these into 2 columns for word 1 and word 2. Now we can break one column into 2, separate one column into two by using the separate function. Very convenient function that comes with R. So what we do is we take Sherlock Bigrams, and we're actually going to modify it in place. So we do Sherlock Bigrams is going to be created from Sherlock Bigrams, but we're going to pass this through the separate function. And what separate function does is the first argument is the column that you want to separate, and then you pass in now a vector of the names of the sort of n columns that you want to separate out to. So in this case we're separating into two columns, which will be called word 1 and word 2. Next, you need to say how you're going to separate. Now in this case, it's a space, one space between the two words in the bigram, and so we can just use sep equals space, and that's a very safe thing for us to do. So if we then look at Sherlock Bigrams to see what's created, what you'll see now is it's going to have separated out the bigram. So now instead of them both being in one column called bigram, they're now been separated into a column called word 1 and a column called word 2. Now that we've separated out the bigram into individual words, we now need to remove the stop words. Now before we would use anti-join, and we used anti-join basically to join together two tibbles where we've only resulted in the rows of the first tibble which did not exist in the second tibble. Now in this case we can't use anti-join directly because there's no way for the anti-join function to know that we're really looking for not in word 1 or not in word 2. So we're going to have to do this using filters. Now we can use filters using the in function. So first thing we need to do is load up our stop words. So we're going to do data stop words. And then what we'll do is we'll take Sherlock Bigrams. We will then create it from itself, where we have now passed Sherlock Bigrams through the filter. And what we want to do is we want to filter out all of the rows where word 1 is not, that's what the exclamation mark means, in with a percent, stop words word. So this is saying give me all of the rows where word 1 does not appear in the word column of stop words. Now of course that would be enough for word 1, but we also need to do this for word 2. So also filter out all the rows where word 2 is also not in stop words word. So it's two filters, one after the other. And once we've done that, we now run this. And now what you can see is we now have bigrams where we don't have any stop words within the bigrams. Now what you can see when we look at this is there's actually quite a few rows where we get NAs, and we're getting NAs here because when we tokenized on bigram, the empty lines, or the lines that only contained one word, got turned into NAs. Now obviously we don't want these NAs within our table, so again we can filter out the NAs. We're going to use the filter function again. So in this case we're going to take Sherlock Bigrams, and again we'll sort of adjust this in place because we don't need to save the unfiltered version. I'm going to pipe this through the filter again, but now we're going to say where it is not is NA, word 1. So in other words, this is saying filter out all the rows where word 1 is not NA. And of course we have to do this as well for word 2. So another filter, not is NA, word 2. And again, if we look at now the result of that, if we run this through, there we are, we can see now we've removed those NA columns. Now finally, and I think this is a definite exclamation mark finally, we want to rejoin the word 1 and word 2 columns to create a single column called bigram, because we want to analyze these as bigrams. Now separate is how we separate one column into two or more Unite is the function we use to unite two columns into one, or indeed more than two columns into one if you wanted to. So again, we're going to take Sherlock Bigrams. We're going to create it from Sherlock Bigrams, but now we're going to pass this through the unite function. In this case, we're going to unite into a column called bigram the values in the word 1 column and the values in the word 2 column, and we want to join them together using spaces as the separator. So you can see this is almost like the inverse of when we did the separate. When we look at the result, this is now the cleaned result. So effectively we now have Sherlock Holmes, Sir Arthur, Arthur Conan, Conan Doyle. So this is how we've tokenized on bigram, removed all the bigrams which included a stop word, and also removed all of the NAs and rejoined them back into bigrams again. Quite a lot of work to get to one point, but actually now, rather than me do this step by step, I can just show you this as a single pipeline, because it's easier just to do it as one long pipeline. So we could say that Sherlock Bigrams was created from the original Sherlock tibble, which was downloaded from Project Gutenberg, and then just mutated with the line number. We do the UnlessTokens to create a bigram column from the text column, where we're using n-grams as the token and n equals 2. That was then passed into separate, where we then separated the bigram column up to create a word 1 and word 2 column using separator of a space was how it was being separated. Then this was then passed into a filter where not word 1 was in stop words word, which was then passed through another filter where not word 2 was in stop words word, which was then passed through another filter where we say word 1 is not NA, which was then passed through another filter where we say not word 2 is NA. And then finally, now that we've done this, we can then unite into a column called bigram, word 1 and word 2, using a space as the separator to unite them. And then if I show you the result, it'll be exactly as we had above, but now just in a single pipeline to make it easier to sort of copy and paste and reuse. There we are. Now obviously if you wanted to use trigrams rather than bigrams, it would be very similar, except here you would have n equals 3, and then you'd have extra words here. So instead of having word 1, word 2, you'd have word 1, word 2, word 3, and then you'd have to filter on word 3 with stop words. You'd have to filter on A with word 3, and then you'd unite word 1, word 2, word 3 at the end. And you'd probably call this trigram rather than bigram if you wanted it to be really correct. So okay, we've now created, finally, our sort of tibble of tidy bigrams. What we can now use it for is we can now do the same kind of counting and analysis that we were using in the previous parts of this workshop. So for example, if I wanted to count the number of appearances of various bigrams, I would just use the count function. So bigram counts we could create from Sherlock Bigrams, piped through the count function where now we're counting the bigram column, and yes, we still do want to sort of sort this. And so by doing this, we can find the most popular bigrams. And yep, as you'd probably expect, Sherlock Holmes appears the most number of times. But actually, look here. St. Simon, Baker Street, Lord Street, Red-Headed, Hosmer Angel, Miss Hunter, Irene Adler. These appear as well. And indeed, what you notice is that by counting bigrams, it's actually a really good way of finding the names and places. Swandam Lane, Dr. Grimsby. It's kind of like, it's a very useful way if you wanted to sort of like scan through and quickly find important places, Leadenhall Street, Miss Turner, or important people. You can do that just by counting the bigrams, a little bit quicker than reading the entire text. You can also find things which are very common, commonly described within the text. So for example, we could find here, there's something that's commonly described. So we have Hosmer Angel, Opium Den, Orange Pips, lots of things pop up, and sort of like, aha, I can see this writer is commonly describing things with various adjectives. Holmes quietly, Holmes answered, Holmes shook appeared a few times. Now, we could also investigate this in more detail. So we see things like street names appear quite commonly. And so what we could do is we could basically try and find all of the street names that pop up. Now, we could do this by filtering on street names. And the way we could do the filtering is filtering on word 2 itself. So we'll do this by actually breaking apart the filter that we created before and adding in an extra filter on word 2 that picks out just the street names. So if I go back to this filter up here, what I could do, I'm going to copy and paste this just so you don't have to watch me type this all out again. If we wanted all of the Sherlock streets, so all the streets which appear in Sherlock Holmes, what we want to do is we want to find all of the bigrams where the second word is street or st, because the streets are going to be called something street or something st, where st is short for street. So what we want is a filter somewhere around here. Maybe let's put this before we do the unite, where we're going to say filter all the rows, where we're going to string detect word 2, so where word 2 matches a regular expression, where we can start, it must start with an st, just in case we're going to find an st elsewhere in it. It might possibly have reet after it, so 0 or 1 of them. So that would mean it starts with an st, 0 or 1 reets after it, and that finishes the word as well. So that means that there's nothing else that comes after street. When we add that in, and then reunite things, and then let's look at Sherlock streets. There we are. You can now see you've got Baker Street, Avenue Street, Baker Street, Regent Street, Baker Street, etc. And of course what we can then do is we can then count them as well. So indeed what I probably should have put the count at the end here. Let's put a count bigram sort equals true. Run that again. And there we are. So we can see Baker Street appears the most times, but actually the same number as Lord Street, and there's Neville Street, Leadenhall Street, etc. So these are probably the most prominent streets within this particular book. Now that's taken us all the way through quite a good chunk of the n-gram section. We're now all the way down to the viewing correlations part. So here, visualizing correlations between words. Now we can go far beyond just counting, the number of bigrams or n-grams appear. We can actually now draw graphs that visualize the connections and correlations between words in the text. To do this, we need to tokenize on bigrams, but now we don't want to unite those individual word 1 and word 2s back into a single bigram column. We want to leave word 1 and word 2 as separate columns, and then ask count to count the number of times each word 1, word 2 pair appears. So how are we going to do that? Well, it's this code here, but I'm going to sort of take you through it as I'm writing it. So let's create a new table called bigram counts. And we're going to create this from our original, not tidied, basically straight from Gutenberg, but with the addition of line numbers kind of tibble, which contain the original sort of Sherlock Holmes text. We're going to UnlessTokens again, and this time we're going to put the tokens into a column called bigram, tokenizing the text column, and again we're using token equals n-grams because we're going to tokenize in n-grams, and n equals 2. We will next pass this through the separate function again because we want to separate the bigram column into 2 columns, which we're going to call word 1, word 2. And we're going to use the separator is going to be a space again. So that will separate each. If I can type, I can never type. Here we go. Separating by space. Now, of course, we want to apply those filters again. So we're going to be filtering word 1 is not in stop words. And of course, we're going to be filtering again so that word 2 is also not in stop words. And of course, there'll still be some NAs left over just as before, so let's make sure we get rid of those NAs as well. So not is .na, word 1, pipe through filter, not is NA, word 2. And now that we have basically this setup where we have word 1 and word 2 are the two words in the bigram, we can now use the count function. And now instead of using count where we're counting just one column, we can tell count to count 2 columns. And we do that by passing the 2 columns one after another into the count function. And what this does is it tells count to count the number of appearances of pairs effectively between the two. So Sherlock Holmes would be counted as one thing, whereas Holmes sat would be counted as another thing. Let's see what this gives us. Oh, and of course I should view it as well, otherwise we can't see what we've got. Okay, so what we have here is you can now see Sherlock Holmes appeared 91 times, Baker Street appeared 26 times, Hosmer Angel appeared 17 times, etc. Now we need to convert this table into what's called a directed graph. A directed graph is one where the nodes, in this case these individual words, are joined together with edges. And the edges basically, there's an edge between Sherlock and Holmes because they appear, and the weight of this edge will be the number of times it appears. Now there's a nice function which comes in the iGraph package which is called graph from data frame, and this will automatically create a directed graph from a tibble that looks something like this. So let's go in here, let's bring in this package called iGraph, and we're going to create this graph by basically taking bigram counts, which we just created above, and we're going to one thing we do have to do is because there are so many words in here, we don't want to be creating graphs which have millions of edges on them because they'd be impossible to visualize. So let's make sure we filter out to make sure only the pairs which appear more than or equal to 7 times. But once we've got that, we can just pass this straight into the graph from data frame function, and it's clever enough to go, aha, you just have 3 columns. These are the node names, the first 2 columns, and the n column is the weight of the edge, the number of times that those things are connected. Once I've created bigram graph, it is just basically a directed graph bit of data. So if we just run this through, you can see this is the bigram graph data, and it's saying that Sherlock Holmes is connected, Street Simon is connected, Baker Street is connected, etc. So you can see it's built these connections between these words that are nodes. Now, of course, we can't look at the graph as this text. We want to actually graph it and make a nice pretty picture from it because it's much easier to analyze. And we can do that using the ggraph package. So I'm going to bring in the ggraph package, which basically draws these sort of directed graphs. And it's very simple. It has the same kind of grammar actually as ggplot. So what you do is you call ggraph on something which is a graph. So in this case, bigram graph is a graph. And we're using layout equals fr. Don't ask me why it works when we use this. And this is kind of like the aesthetic in many ways. And now to this, we then add on things. So geom edge link will then add in lines which link together the edges. Geom node point would add points for all of the nodes, all of the words. And we want some text on each node. So geom node text would add that text in. And the aesthetic for this added on text is the label, which is the thing which is actually the text written to the screen, comes from the name column. And the name is the name of the node. It's sort of created for you automatically. And then we want to do the vertical justification is 1, horizontal justification is also 1. Again, you can play around with this if you want to explore with it. And there we are. This is now drawn the graph. So you can see here we have Sherlock Holmes is connected, Laughing Holmes is connected, Holmes Remarked is connected, Clare Street, Lord Street, Neville Street, Simon Street, etc. But at the moment we see the lines. We don't know which way that it's connected. Does Sherlock come before Holmes? Probably. But does Holmes come before Laughing, or does Laughing come before Holmes? We'd want something where we can draw arrows to show the direction. Now, we can do that by looking at the options online for how we can sort of tell ggraph what to do, or you can compare to graphs you like. So I've linked into the notes a graph I particularly liked, and what we do is we can basically copy the aesthetic and the setup from that, and that's generally how I recommend you draw graphs. Find one you like and then copy the options of it. So in this case, we're going to do a G-graph. This is one I really do kind of like. In this case, we're going to take bigram graph. Again, layout equals FR. I found when I experimented with different layouts that it actually caused my RStudio to crash, so do be a little bit careful when you're doing that. In this case, we're going to do geom edge link and pass some options to it. So we're going to pass an aesthetic into this. And in this aesthetic, we're going to say edge alpha. So that's basically how transparent it is equal to the number of times that it appears. So the more times it's been this pair exists, the deeper it's going to be, the more opaque it's going to be. I'm going to say show legend equals false, just to make sure the legend is not shown on the edges. And then also with the edges, there's quite a few things to put on here. We want an arrow. The arrow is going to be equal to a grid arrow. And this arrow is going to be closed type. And the length of the arrow is going to be just 2 millimeters. Okay, be very careful when you type these. And then the end cap of the arrow, so this is still all looking at the edge, is going to be a circle. So we're going to draw a circle on the end, which will just be 1 millimeter in size. And again, it takes a bit of time to practice and get these things right. Double round bracket to close. Now we've done the edges, we now need to draw the node points. So these are the nodes themselves. Let's make them light blue in colour. And let's make their size equal to 2. I believe that's 2 millimeters. And then finally, we're going to add on the node text. The aesthetic for the node text is as pretty much as before. The label comes from the name. But in this case, the size is also equal to 2. And then finally, we add on theme void, which tends to clear everything out and seems to make it work well. When we run that, we get a much nicer looking graph, and now you can see the arrows point in the direction of the words. So Miss Hunter, Miss Stoner, Stoke Moran, Lord Street, Neville Street, St. Simon, etc. And Sherlock is there, Sherlock Holmes, Remarked Holmes, Holmes sat, and Holmes laughing. And we can see Sherlock Holmes is by far the most deeper coloured, most opaque, because it appears the most number of times. Now, we can see from this graph that Sherlock Holmes is a heavily used bigram, but we can also get more information about surrounding words. So, for example, you can see it probably is Sherlock Holmes laughing. Maybe those things go together, or Sherlock Holmes sat. You can also find common phrases. Like if we look through this, we can see there might be linked things. So what have we got around here? There's Baker Street and there's Henry Baker. And here we have Red-Headed League. And indeed, the Red-Headed League is an important thing within the Sherlock Holmes book. So again, we can find the things appearing that might be important within the actual book by looking at these connections between words. Now, because we have this finer control, we can actually increase the number of points we view. So in this case, we actually filtered on having this with 7, I think it was. If I just take the copy of what we had above. So we create a bigram graph by filtering on 7. But actually, now that we have a better graph, we can maybe filter on a slightly smaller number. So let's put this on top. And now maybe let's filter this with maybe 3, so we get many more bigrams visible. There we are. So you can now see many more things popping up from the book. So we have Sherlock Holmes pushed, Sherlock Holmes observed. And you can see traces amongst the words, days ago, months ago, breakfast table, dressing gown, left-handed, etc. And sometimes you can find little patterns here. So, dear Watson, and dear Sir, Sir George Burwell, dear fellow. So again, it's kind of interesting as you sort of look through this. Pretty cool. So that's now taken us through all of the correlations part of this particular section of the workshop. And we have essentially 2 exercises for you. One is I want you to create a similar bigram graph for your chosen book. So put your book in there and see what bigrams, what connections you can see. And then the second exercise, I want you to create a bigram graph from the Hamlet soliloquy we looked at the beginning of this workshop. Don't remove the stop words, because actually to be in this case is quite important. And also I want you to draw the graph of all of the bigrams, so don't filter it at all. So this will show all the bigrams in the entire thing, and that might be an interesting graph. So I'm going to give you some time now to have a go at these 2 exercises. Put me on pause while you have a go, and then, when you come back from pause, I'll show you both of the answers. Okay. So you've come back from pause now, and I'm going to take you through, an answer. There are lots of different answers. This is just the one I'm showing you. So, go into a new R session. Again, I'm going to download The Hand of the Baskervilles just for sort of continuity, what we've had before. So this is basically book number 2852, and we're going to create a bigram counts for this. So it's going to take the Hound book. We're going to pass this through UnlessTokens like we did before. And we're going to put the result into the bigram column because we're analysing the text column. But now the token is not a single word. The token is in n-grams, where n equals 2. Then we're going to separate the bigram column out into 2 columns, which we're calling word 1 and word 2. Where the separator is a space. Next, we're going to filter out all the times where word 1 is not in stop words word. We'll filter out all the times where word 2 is not in stop words word. And then we'll filter out, there's a few of them here, not is NA word 1. And then finally, filter out where not is NA word 2. Now that we've done this, we want to build the counts of those pairs of words. So counting up word 1 and word 2 and sorting it. In this case, I'm going to say, yep, sort equals true. Okay, now we've got the bigram counts, we can now create the bigram graph. And this we can create from bigram counts. But we're going to filter out here all of the pairs where there's more than equal to 3. So we don't want anything where the bigram appears less than 3 times, because there'll be too many things to graph. And then we're going to pass this into that graph from data frame as we did before. Okay, now that we've got this in bigram graph, we can now call ggraph on this. So ggraph, bigram graph. I could have piped this into ggraph as well. Layout equals fr. And we're going to do geom edge link. So making this look nice and pretty as we had before. So the edge alpha is going to come from the value, the number of times it appears. Show legend is false. We want to make sure that the arrow is drawn, and that's going to come from a grid arrow of type is closed. and the length is going to be 1 millimeter. And the end cap is going to be a circle of 0.5 millimeters. Then we're going to add in a geom node point, and that color is going to be light blue like we did before. And the size of that is going to be 0.5. And then finally, geom node text will be added to draw text for those, where the aesthetic, the label is going to come from the name column, and the size equals 1, and then we can then clear the void, clear the theme. Okay, let's see what this gives us. If I've typed this correctly. There we are. So maybe a little bit small to see on the screen, but you have all of the parts here. So that's Henry Baskerville, and then another word there, a bit small on my screen, I can't read that, but you know, if we sort of save this out as a picture and then sort of viewed it later, we'd be able to sort of view it more at a larger scale. I'll show a new window. No, that didn't let me do that. I was hoping we could zoom in on that, but that's not going to happen. Okay, so now we're going to look at exercise 2. And exercise 2, we wanted you to do the same thing, but actually for all of the bigrams within Hamlet's soliloquy. So it's going to be the very, very similar process, but now we're going to take Hamlet's soliloquy and download it from the URL that I gave you. So I'm just going to copy and paste this so that we have this all in one place. You don't have to watch me get this wrong. Now it's pretty much the same as we did before. So we're going to create bigram counts like we did before. So I'm going to copy this down. But of course, we're not analysing the Hand of the Baskervilles here. We're now analysing Hamlet. So again, it's the same thing, UnlessTokens, separate by bigram, but in this case, we don't want to filter out the stop words. So I'm going to remove these filters on the stop words. We do want to filter out the NAs, so of course that's still important, and then we'll create the count here. Next, we can do the same thing as before, it's just creating exactly the same graph. So again, I'll just copy and paste this rather than have you watch me type it all out. But the only difference we're going to have, as I said, don't filter it. So we don't need to filter out everything where n is more than 3. We're going to draw everything here. When you have a small text, like the soliloquy is, it's okay to draw these graphs with all the bigrams because, you know, there's not that many of them. You're not going to overload the computer. And there we are. This is all of the bigrams from Sherlock Holmes, and indeed I have written this down in the answer so you can see this. I'll zoom in on this one. So you can see things like you can actually follow the lines of text in this. Proud man's contumely. Where is to be or not to be? There we are. To be or. And there's the not somewhere. And then you have phrases where you can see something that's not used much. When he himself might his quietus make. And then you've got make cowards of, and then somewhere there will be us all moving off. So again, you can follow in this kind of diagram these little like parts that come out. So again, this line here, this shuffled regard, their currents turn awry. So it's interesting in the way this kind of graph can sort of give you information or insight into the poem. So very cool. So okay, so that's taken us through to the end of the exercise. That's the end of this particular section. Thank you for taking part. We've actually finished the workshop, and so the next section is just the conclusion and summary. I hope to see you there.